Alright, so welcome to another video, and in this video I'm going to go over this digit classification project. So as a brief overview, this is using the MNIST dataset, which is a large dataset of grayscale images of handwritten digits 0 to 9. There's this other dataset called the Fashion MNIST dataset, but that's for clothing, I'm pretty sure. But this one is a very common beginner project, so it fits me. Yeah, so for example, the images are like this, and basically the background is like black, whereas the digit is written in white. So, and you can clearly see different pixel intensities. So that's going to be beneficial. That's going to be useful, like if we're focusing on a region and we want to pick, and we can look at the different pixel intensities of like, because a grayish pixel would be more of like in between 0 and 1. If we say a black pixel has a value of 0 and a white pixel has a value of 1, we would like in between would be grayish pixels. But yeah, so that different pixel intensity is going to be useful. And yeah, so each of these images, by the way, are 28 by 28 pixels, which is common for the MNIST dataset. And yeah, so FYI, this is using PyTorch if you read the title. So you're going to want to import everything you're going to need from PyTorch, from Torch. And yeah, so for the device, I'm currently on a Mac, and I don't really have any NVIDIA GPUs. And even though I'm on a Mac, I also don't have MPS. But so I'm going to have to resort to my CPU. But it works pretty well. It's just I guess it's just probably gonna be slower than other people with it who use GPU, but it works. So for the data set now, we want to, I'm just gonna write. So so basically this is downloading the training and testing datasets from Torch Vision.datasets. So it's getting the MNIST datasets, the dataset which is pre-split into this training and testing portion. So where the training portion contains like 60,000 images, and the testing portion contains like 10,000 images. So here we're just downloading those datasets, and we want to convert the images to tensors so PyTorch can use it more easily and efficiently. So yeah. So here you can see like we have 60,000 training images, and we have 10,000 testing images, and all the images are 28 by 28 pixels. Yeah, so then for the data loader, well, I just arbitrarily chose 100 image tensors to be used per batch, and we want to shuffle them because we want it to be more randomized, so the model will like not somehow start to rely on like order to predict, so just more randomized. And then for the neural network, the actual neural network, this is using a convolutional neural network, which is better for like image and video processing, and compared to something like a RNN or recurrent neural network, which is better for like text data and natural language processing. But CNN is better for like images and stuff. So I just chose to have 3 convolutional layers, and with a kernel size of 3. So the kernel is like a small window or a matrix that goes over your image, slides over your image to extract like features from your image. And so a kernel size of 3 is pretty common, but like with the default stride of 1, it'll make your image reduce by 2 pixels in width and height. So padding compensates for that by with a padding of 1, your essentially adding 2 pixels in total on the width and height, because one on each side, and that basically helps to preserve like features on the edge of the image if we have any, and the spatial dimensionality or whatever it's called. And so after that, you want to apply your activation function. So ReLU stands for rectify linear unit, and it's like the most common activation function, I'm pretty sure, or the most preferred over like other ones like hyperbolic tangent or sigmoid, because people say tanh and sigmoid have vanishing gradient problems where during backpropagation your gradient will approach 0, so you won't be learning that much from your data anymore, and like you can't really update your weights and biases anymore. But yeah, so ReLU activation function helps to introduce nonlinearity, so your model can learn more like complex features and stuff. Then this is a pooling layer. So pooling layer, it like reduces the size, and max pooling 2D basically takes the maximum value over a region. So like for example, in this case, like if we had like some white pixels and gray pixels and black pixels in a certain region, we would just pick the pixel with the highest value. So say our white pixel was at 1, we would just choose 1 to replace replace the whole region we're looking at right currently. And that's good because you can extract like the most intense feature or most intense value or whereas something like average pooling would just take the average of all those pixel values, like and then for our dropout layers, I just chose 1/4 of the neurons or feature maps to be disabled for less overfitting, so it can more generalize more, so it doesn't rely on specific neurons more than others. And then we have forward pass here. You can just read the comments, honestly. I'm kind of tired of talking so much. And so here is the actual model. I will add some stuff actually. So this is using the Atom optimizer with a standard learning rate of 0.001. The SGD optimizer, which is the stochastic gradient descent optimizer, which stochastic meaning random and gradient descent meaning you're trying to find the lowest value of your loss function, which compares the target value and the prediction value. But yeah, I'm gonna have to look into more of the really difference between Atom and SGD. And for the loss function, this is using the cross entropy loss. Cross entropy loss is also sometimes called the log loss because it uses a logarithmic function. So the more error you have, even a slight change in error is gonna create a big difference. So it's gonna punish the model more for just small error increases. So yeah. And it has softmax built in, so softmax is like converting the logic or raw outputs, I'm pretty sure, to like random to probability distributions. Because probability distributions, if you had like, for example, say, because if you say like see something in like you have a 70% chance of it being a dog or 30% chance of it being a cat, you would of course go with the dog. So that's what softmax sort of does, creates a probability. And then here's a training loop. You can just read the comments, honestly. And then So here we're just training it for 15 epochs, or 15 passes through the data. And here's to visualize it, the actual predictions down here. So we're using matplotlib, and we're creating subplots. And if we basically get, if some prediction is wrong, we're gonna color the text like red. Otherwise, just keep it as normal. Yeah, so I already ran all of these cells beforehand, so we can just rerun these. So right now we're displaying 5 images. We can go as like 10. See how well we do if we get anything wrong. Yeah, so as you can see, it's pretty accurate actually. Let's go with. I don't know. I don't know if I'll ever get. I had this one time where I got like, I think either a 0 mixed up with an 8 or something, but anyways, yeah, it's pretty accurate. Yeah. So basically that's this project, I guess. That's the that's my very simplistic explanation of this. So hope you guys enjoyed this video, and the code will be in the description, and don't forget to subscribe and like.